Imagine you have built an incredible language model. It nails every benchmark in your Jupyter notebook with crisp summaries that read like sonnets and image generation prompts that yield gallery-worthy art. Yet, when you try to show it to your team, you find yourself wrestling with HTML, CSS, JavaScript, and coarse errors. The demo you planned for today suddenly smells like endless debugging. Hey everyone, welcome to the NIAT masterclass on building LLM apps with Gradio, from prototype to deployment. I'm Suvojit, Senior GenAI Engineer at EXL. If you've ever felt your model's brilliance dimmed by the pain of building a web interface, you're in the right place. Today, we'll transform that knot of boilerplate into a smooth, interactive demo, and you can spin it up in pure Python. We'll begin by exploring why Gradio turns days of front-end work into minutes of code. Then, we'll master the art of prompt engineering for both text and image tasks, build 2 live modules in tandem, introduce an AI-powered editing workflow for refinement, and finally, deploy your cohesive app to the cloud with just a few simple steps. Let's get started by taking a peek at what we are going to build. So this is the Gradio UI that you see on the screen. As you can see, it has these components for generating an image where you can enter some text. You have an option to upload an image, and you also have an option to view the image and edit the instructions. So let's take a look at in brief as to what we can create with it. We can generate an image by giving it some instructions. In this particular case, we want to generate an image of a salmon on a plate. This is for, let's say, a restaurant. Now, this image will be generated not just based on what we entered, but this prompt will be engineered further by the LLMs running at the backend, and it will create a more detailed prompt that you'll soon see on the screen. This will help to generate a much better image as you see on the screen. It has more details than the prompt that I entered. So for example, as I have mentioned about it being a professional photo with spinach, lemon, and some other basic details. The engineered prompt has added far more details, like adding a slice of fresh lemon. Then it has mentioned about the exposure, the type of photo, the background, and also how the stick will, how it will appear on the screen. Thus, it has generated an image which is comparatively much more detailed than it would have been without the current prompt. We also have an option to edit this image by giving it some instructions which will change the aspects of the image as per those engineered prompt. But we'll talk about this in the next parts of the session. Now, what you saw on the screen was running locally, but we also want to deploy it in the cloud. So before we begin the session, let's look at all the things that you'll need. You'll need access to cloud GPUs and specifically NVIDIA GPUs on platforms like Runpod. You'll need a Hugging Face account. You'll need access to libraries and install them, for example, Gradio, scikit-learn, transformers, and PyTorch. You'll also need large language models like Wen 2.5, 7 billion model, and you'll also need image generation models like Stable Diffusion. Let's take this scenario. You have trained a model that works flawlessly in your notebook. Then you demo it, and suddenly your focus shifts to front-end bugs and deployment frustrations. Non-technical colleagues or stakeholders can't replicate your environment. Browser quirks slow you down, and your project momentum stalls. Now let's understand what the challenges are with the existing workflow. Building dynamic UIs with interactivity from scratch can be a challenging task. Integrating multiple models into a single interface can be a complex process. And building a clean, reactive user interface from scratch requires both JavaScript and backend skills. Our mission is to erase these blockers so your innovations shine immediately. So let's understand some foundational concepts. Traditionally, web stacks offer flexibility at the price of speed. Writing Flask routes, crafting HTML forms, and debugging cores. By the time your user interface is up, the model's insights already feel old. Gradio flips this paradigm. In just 2 lines of Python, you map any function to a browser-based interface. Gradio provides 3 pillars: interface for single function demos, blocks for assembling custom workflows, and chat interface for chat-based interactions. Plug in components like a text box for input, an area for output, buttons to trigger actions, and you have an interactive app, all in Python. No need to juggle multiple languages or frameworks. So as you can see on the screen, we have a simple block diagram to understand how Gradio works. Let's take a look at it. It has input components, parameters, your function, return value, and output components. Let's understand them one by one. So when users interact with the Gradio interface through components like text box, numbers, and images, Gradio does pre-processing at the backend. Text box for string input, number for integers, and images for image uploads are already handled by Gradio at the backend for the user. Gradio automatically converts these user inputs into input and the structure of the user interface. Other than that, Gradio also converts functions into appropriate types based on their input and output. When you define a regular Python function, or let's say an LLM API call, Gradio passes the process inputs directly to this function. It will return the value in a way depending on the output type, the data type in Python. So it can return a single value, which could be a float, multiple values, and Gradio also does post-processing as per need based on what you have created. So once Gradio has processed these outputs and the output types, it will show these output components on the screen with number for displaying the numerical results, gallery displaying one image or multiple images, and the key benefit of this user interface built with Gradio is that it handles all the data plumbing between Python and the user interface. So what are the key benefits? The key benefits are that Gradio handles all the data plumbing that is needed between the user interface and your defined functions at the backend. This helps ensure that you do not need to do the data plumbing yourself. You write only the core logic and Gradio handles the rest of the work for you. So let's take a look at what are the types of interfaces that you can build with Gradio. As you see on the screen, Gradio has a standard interface of inputs that determine the outputs. We have output-only interface, for example, for GANs. We have input-only interface, and we also have a unified interface with every possibility that you can build in Gradio. Let's understand them one by one. First of all, the standard interface that we build. It can be built for mostly it's the most common type of user interface where you can take an input, process them, and just show the output. For example, you upload an image at the backend, it classifies that image and then shows you the answer. And you can also build text summarization with it, where you just input some text, let's say from a book, and it summarizes that text and shows you the output. It's a very simple interface and also the most commonly used one. Let's take a look at the output-only interface. Why output-only interface? Is it useful when you can build both? Well, output-only interfaces are useful for GANs, for generative adversarial networks, where you do not really need a function for the input to run. You do not need to input anything, but it is running in the backend where it is showing you the output in real time. Generative adversarial networks which generate art, where you can simply click on a button and it shows you different forms of art that you can download, and also noise-to-noise image generation is quite useful for this particular user interface. Now, let's understand the input-only interface. This is less used, but it's mostly used for data collection as a data collector, where you have certain input segments that you need to fill and submit, which gets populated, let's say, in a backend table, be it an SQL or a NoSQL table. So that's an input-only interface. And lastly, we have a unified interface. A unified interface where you have all possible components at the same time and also at different points. This is what we have also built for this particular demo, where you not only have an input or an output, but multiple of them, and they sync based on how you're presenting and building the user interface. This is useful for not just simple text generators, which you can build in the first use case, but also many other use cases, including this one. Additionally, Gradio lets you share links very easily with stakeholders. You can easily generate a shareable link that is publicly available and usable by anybody, and you can also protect it with a password by ensuring only certain people have access. This makes it ideal for stakeholders, and DevOps is not required. Now, let's dive into prompt engineering. Even the best large language models need a clear director. A minimal prompt like "summarize this" is too vague. Instead, structure your prompt around 3 pillars. Role. Define who the model should emulate. Example, you're a legal analyst. Context. Supply the relevant text or data. And finally, the instruction. Specify exactly what you want, in what format, For example, return a bullet list of key obligations and deadlines. That precision turns generic outputs into focused, actionable insights. Let's take a look at this example. We have a prompt, let's say, make a picture of a biscuit. That sounds simple, right? But it's also vague. So what do we get? A plain generic biscuit on a white background. No emotion, no style, no story, just a basic output. Now let's try it again, but with a well-structured prompt. Here's the improved version. Let's say we define it this way. You are a professional food photographer. Create an ultra-realistic 8K image of a freshly baked chocolate chip biscuit on a rustic wooden table with warm natural lighting and soft shadows. Now let's think about what happens. The model steps into a defined role, a food photographer. The context is rich, a chocolate chip biscuit, a rustic wooden table, and a well-lit setup. The instruction is precise, ultra-realistic, 8K with warm light and soft shadows. The result, visually stunning image. You can almost smell the biscuit. It has texture, depth, atmosphere, and it feels like it belongs in a gourmet magazine. That's the power of prompt engineering. Even the most advanced models still need a clear director, and that director is you. So we all saw the importance of prompt engineering in generating a proper detailed image. Now let's do a hands-on on the same. As you can see on the screen, in order to proceed with this lab, we need certain requirements. Let's look at these requirements. You need these libraries along with Python 3.12 installed in your virtual environment. How do you do that? You have this requirements.txt file where you have the list of libraries and you have a setup file. This setup file will make it easy for you to install all of these requirements along with other dependencies, including setting up your Hugging Face account and also setting up Git LFS as needed. Starting off, this will install Python 3.12, which is important for this particular hands-on. Other versions of Python may not work properly with these specific libraries. After that, you need to log into Hugging Face and set your Hugging Face token using this setup file. And it will install all of the requirements file. It will install some extra required libraries that are not there in requirements. It will log into Hugging Face and get everything ready. Now that you're done with the setup, let's go back to the code and understand how we can work on prompt engineering. Starting off, we're importing the necessary libraries. For example, config parser, which will read the values from config. We have llama CPP, which is a CPython library that can load LLMs in quantized format at a much higher speed, that is much more tokens per second. So when you interact with the large language model, it is going to be much faster compared to traditional transformers library or with any other library. You also have LangChain core prompts. So this is for formatting the prompt. You may or may not need it depending on which model you use and how you plan to use it. We'll look at these details as we go forward. First, we load the config. What are the details that we need to save in the config that are needed first? So let's take a look at the config that is needed in order to save our values and use them in these variables. What are the values that we save in the config? First, we need to download a large language model and save it in a path, which will be mentioned in the config. This is necessary for the prompt engineering step, where the large language model should be sufficient enough to do the prompt engineering, but at the same time, it should be able to load in the necessary VRAM that you have. In this particular case, we have chosen Qwen 2 7.5 billion parameters instruction fine-tuned model. The reason behind choosing this model is that this specific version of the model that is instruction fine-tuned works really well on a host of topics, especially in describing them and elaborating on them in detail. This is quite helpful for prompt engineering, as no matter what kind of prompt you enter, be it a smaller one, be it a detailed one, it will always be able to handle those topics and create a more detailed prompt that can generate a better image. Then we are defining all of the other things like the output directory where you're going to store the image outputs. We have many other things saved here. What are the things that we need for prompt engineering here? In prompt engineering, we are taking the model. We have the context length, the batch size, the maximum tokens, and the temperature. Let's understand how to set these values so that your project can work really well depending on your use case. When it comes to the context length is quite helpful when you're having a longer chat history. For example, if you're talking to, let's say, a chatbot and you have a series of conversations, the longer your context length, the more easier it is to remember your entire conversation and respond back to you. We'll go through in detail as to where context length is helpful in our use case as we move forward. Meanwhile, let's look at the other variables. The batch size, this is for determining how many inputs you can feed into the LLM at one go. So for example, if you're deploying this, which we'll see later on, in a way that it needs to process multiple inputs at the same time, this will work really well and generate you multiple images. Maximum tokens, this determines how longer you're willing to go, how bigger you're willing to go with your prompt. If you want your prompt to be much smaller, you can limit this and it will generate maximum tokens of a much lower length. So your output prompt will be of less words. So we also have the temperature. What's the temperature? The temperature value between 0 and 1 is responsible for how strongly your image is generated close to your prompt or how creative it is. For example, you want to generate the image of a cat and you have given it some instructions what it looks like, what the background looks like. Now, if you set a very high temperature close to 1, the engineered prompt is going to be quite creative. It will add a lot of new details that you did not add and make it really nice. So if that's what you want, or if let's say you want to generate some artwork, then it's quite helpful to have a very high temperature that will add a lot of creativity to your image. At the same time, if you want to generate something very specific, let's say the image of a tool or the image of a product, where you want it to follow exactly your instructions, that way you can set a very low temperature and your engineered prompt is going to follow closely exactly what you described. Hence, the image of the product or the tool or any other item that you're generating is going to be quite identical to exactly what you described. So this is the difference between setting a low and high temperature. Going forward, we are loading the model files. Talking about Llama CPP and how this model works, I mentioned the model is Qwen 2.5 billion. Now, if you want to run your model on a CPU, or you have low VRAM, be it you're running on a GPU or be it you're running on a CPU or any other kind of system, let's say a TPU, you can use Llama CPP independent of the platform and load your model, and it will still work at a decent speed. The way this works is mainly two ways. Llama CPP is a C Python library which is quite fast because of it being written in C++, and at the same time the model is quantized. In this particular case, the model is quantized to Q5km. Hence, the amount of memory required for this is significantly less compared to the original model 7 billion. For example, 7 billion will require around 20 GBs of VRAM or CPU memory, depending on how you're running it, along with some extra buffer memory for storing the prompt and answering your questions and generating the engineered prompt. When you're doing it with a quantized model, let's say for example Q5km in this case, this will require only around 4 GBs of VRAM and let's say an extra additional 1 GB, so total 5 GBs of VRAM or CPU RAM to generate it. Hence, if you are working with a system which has these limitations, you can still get the result in a pretty fast, with a pretty fast response, and at the same time you won't have issues with memory out of error. So this is the use of Llama CPP and a quantized model, and you can see on the screen that we are loading the GGUF format quantized model. It is in two parts because it's a 7 billion model, so it's quite small. There's only two parts, and we are specifying the first part which follows a specific pattern. This will automatically take the next pattern, and likewise it will load the model. Let's look at the next steps. We have a function defined for loading the config. This is taken from config parser and it's reading from the config file that we saw on the screen. Then we are loading the model, which I have stored it in this particular folder, and we are giving it those values that we read from the config. That is the context length, batch size, and another attribute verbose, which basically if you set it to true, then you'll get to see all the inner workings of Llama CPP, how it is loading, if there's any issue you want to debug. Otherwise, you set it to false. Now, we start with the actual instructions for prompt engineering. Into this template, we'll be passing what we enter. So let's look at this in more details. First of all, we are getting the basic details like max tokens, temperature. Then we're defining the prompt. If you see, there are a lot of specific tokens that have been mentioned, and inside that is nestled the user prompt. The reason behind this is that depending on how you use your model, whether with Llama CPP or whether with the transformers directly, you can load the prompt in different manners. You can use the auto models. You can use the auto modules from transformers to automatically load the prompt and format it in the specific format for that large language model. Or you can use Llama CPP and you can specify these tags which are specific to Qwen. If you use a different model, these tags will differ. So you need to check up if you're, in case you're using a different model. For example, let's say Llama 3. Now, we have the user prompt in here, and you have given these instructions like you're a helpful assistant and an expert prompt engineer for AI image generation. Your task is to rewrite the user's prompt to be more detailed, vivid, and creative, specifying style, lighting, composition, and any relevant detail for a text-to-image model. Thus, we are giving these instructions so that it can focus on these aspects of it and expand on the prompt. After this, the assistant will start responding. So if you see the prompt, it ends with I am start assistant. So after this, whatever response is coming from the LLM, and that is how it will be streamed. So we have the stream function here. We have the stream object here which will be run. So we are loading the prompt, the max tokens, temperature, and you have set stream equal to true. What is stream? So in the context of using Llama CPP, just like when you're using a chatbot online and you type something and it does not wait for the entire text to be generated, it keeps streaming the response. That's the same thing happening here. And it's being done with Llama CPP. You can choose to turn it off in case you want the entire prompt at one go, depending on your use case. Now, we go to the next part, which is basically running the model. We have everything ready, our prompt, all the variables that we need, all the attributes that we need, and we are going to run the model and input certain value, certain details about the image that we want to generate, and it will engineer the prompt and give me a more detailed prompt. Let's take a look at that. So I have the terminal ready. Let's say I'll generate the image of a biscuit packet on a table, a very simple prompt with no detail. Let's see what the prompt engineer does, and we'll be able to see it almost instantly with Llama CPP, because as I said, Llama CPP is a C Python library loading quantized models, so it's quite fast. And we see the streamed prompt here. I'll read this. A close-up image of a beautifully designed biscuit packet sitting on a rustic wooden table in a cozy kitchen. The biscuit packet features a vibrant, pastel-colored illustration of whimsical fairies and flowers with golden highlights accentuating the text and the design element. The table has a warm, amber lighting with soft shadows, casting a gentle glow on the biscuit packet, which is partially illuminated, creating a sense of depth and texture. The background is a blurred, muted color to draw attention to the biscuit packet, and the table surface has subtle crumbs and tea stains to enhance the realism and coziness of the scene. So as you can see, this is a really well-crafted, detailed prompt, which is very ideal for advertisement banners. So let's say you are a part of a company that is working in the advertisement field and you want to sell a packet of biscuits and you want to create a banner for it. You no longer need some kind of a detailed team that is working on these details and then crafting and editing these details. You can simply use AI to craft this prompt and proceed with the image generation. So that's the importance of prompt engineering, and after this we'll move to the image generation step. Now we saw the details of prompt engineering and its importance. It's time now to actually generate the image using the engineered prompt. Let's look at these details. Starting off on the screen, you can see the same requirements installation and the imports. We have imported config parser, which the details of which you saw in the previous part for prompt engineering. Now we'll look at further more details to see how we are generating the image. First, we'll set up the pipeline for stable diffusion. So what's stable diffusion? Stable diffusion belongs to a family of diffusion models which work on the principle of diffusing pixels gradually in order to generate the image. So when you first enter some prompt and you want to generate an image, the way stable diffusion models and other diffusion models work is it first will generate some pixels which will be completely blurry. Then it will diffuse most pixels, increase the entropy of it, and more pixels will get generated over time following a statistical pattern based on the prompt and based on how the model was tuned. That's, in short, how stable diffusion and diffusion models work. Now, to set up this pipeline, let's look at what are the details that we need, how we are setting it up, and how we are generating the image. It's pretty simple. First of all, we are defining a pipeline setup, and inside it, we are first loading the model. So we can either load the model locally or we can load it from Hugging Face. So let's say you are running it for the first time and you don't have the model for Stable Diffusion. In this particular case, it is Stable Diffusion version 1.5, or you can also use other versions. If you want to simply directly run it, you load it with Hugging Face model object, which you can see here, and this will download the model from Hugging Face, save it in a temporary directory, and let you generate it. Otherwise, once you want to have this in a fixed place and not have to download it multiple times, you can save it in a particular folder and just point to that local path. After that, we are loading that model using this Stable Diffusion pipeline. This is a pre-trained model that was tuned by Stability AI. You have the official version Stable Diffusion 1.5 that is available by them. You have also other instruction fine-tuned versions which are available on Hugging Face as well as other platforms which you can use based on your particular use case. In this case, we'll go ahead with the default version directly from Stability AI. You can also fine-tune this, but in most cases we'll not need it. Rather, you'd prefer going for editing image, which we'll see next. Let's look at the next steps. You can run this on different devices. Currently, just like for prompt engineering, we are running this on an Apple device using Apple's MLX framework. Hence, we are using the device MPS, which you can see on the screen. Let's say you're doing this on a Windows laptop with NVIDIA GPU, or a Linux laptop or a Linux machine with an NVIDIA GPU. It is going to use CUDA, and that has to be installed. So likewise, it will automatically set depending on what's available in your machine, and it will move forward. So our pipeline is set up with just a few simple steps. Not much detail is needed unless you want to use some other version of it, or you want to have any other sort of complexities introduced into it, which we'll see later as we go for edit images. First, we are going to create a prompt. This could be a prompt as simple as biscuits on a table, or like we saw when we engineered the prompt. Or this could be a more detailed prompt depending on the user who is generating the particular image. Let's take the example of a restaurant, let's say in Japan, who wants to generate images of fish, specifically salmon, on a plate, and showcase that on an online menu or an offline menu in order to attract customers to dine at the restaurant. So how do we do that? In this particular case, assume the user who is generating the image already has some ideas of how it should be and has given a little more details. But it's still not enough, and it needs to be engineered, which we'll see that in the integrated demo. But let's see how well this prompt can generate the image. We have mentioned these details about the salmon steak with some spinach, lemon, steam, super realistic soft light, exposure blend, medium shot, muted colors, dim colors, soothing tones. All of these will be factored into generating the image by Stable Diffusion. After this, we have defined the image generation pipeline. We are simply going to use that and generate the image. We'll save that particular image in the particular output directory, and we'll see. Let's see how it works out. Now, we also need to understand how these differences in prompts helps us generate a better image. Let's say we enter just salmon, and we run it and try to generate an image, versus we generate it with this detailed prompt which could be engineered, which could have more details set by the user, and compare them and see how well Stability AI works with their model. So while this is generating, at the back end, what's happening is that unlike Llama CPP for prompt engineering, Stable Diffusion does not support Llama CPP. So it is using the default pipeline from transformers and generating the image. So as you can see, the difference in these two images, which is quite clear in terms of what will attract a user more. On the left, you have our image from the engineered prompt with more details about the pepper, about the surroundings and all. It looks a lot more professional and similar to something that you'd see, let's say, on the Instagram page of the particular restaurant. On the right, we have a simple prompt salmon. Now, Stable Diffusion is good enough to generate an image with a simple prompt, but for this particular use case, we need a much better image which is generated with more detail and looks much more professional. And hence, the engineered prompt can generate a significantly better image, more detailed image that is suitable for advertising on their social media. So that's about Stable Diffusion and Stability AI and how image generation works. So far, we saw how to generate images with an engineered prompt. No matter the prompt that we give, it is made more detailed and we generate a very nice and detailed image with Stability AI's Stable Diffusion. Now, sometimes we may not be happy with that image and we want to change some aspect of that image. Or sometimes we might have an existing image of a banner for, let's say, an advertisement, and we want to edit certain aspects of that image before that goes live. That's where image editing comes into the picture. Image editing with AI is possible thanks to the same model Stable Diffusion using their editing pipeline. Now let's look at how that is possible. As you see on the screen, we are loading our usual models. The same models that we have, that is Stable Diffusion, and we are loading the details from the config, the prompt templates and everything. After we have all of these details, similar to how we got it for image generation, we load the model and we define the prompt, this time for image editing. So what are the instructions that we need to give? It's pretty simple. The task of the AI model is to rewrite the user's prompt to be more specific about the edits needed in that particular image based on what the user said. And apart from that, it should also focus on generating only one improved prompt. Sometimes it generates multiple aspects of it. So we need to focus on very specifically those aspects which the user has mentioned with some modifications. That's the input prompt here to the image editing model with Stable Diffusion. After that, we define the prompt with the appropriate tags, and then in the same way, we load the Stable Diffusion pipeline for image to image. Earlier for image generation, we loaded the image generation pipeline. We are loading the same model, but this time with image to image pipeline. What's image to image pipeline? It's basically the same model used to give not just a text as an input, but also the image converted into base64 string as an input. It feeds these two into the model, and using diffusion, it regenerates that image with specific aspects of that image or specific objects or colors in that image altered as per the user instruction. How do we do that? Well, after initiating the pipeline for Stable Diffusion image to image, we are simply going to select the image that we want to modify. It could be a pre-generated image, it could be an actual image, or it could be an AI-generated image that we generated in the last step and we want to modify. After that, we pass the prompt to the model and we run it with Stable Diffusion. This will generate me the modified version of this particular image. How does this work? Well, let's run this. We will specifically run this for biscuits. Let's say I have these options. These are some of the images that were generated. I will run it for the second option, biscuit on a table. And I want to modify this. Let's say I will blur the image, blur the background of the image, blur the background of the image. And I also want to add some more details. Maybe let's say add a tea kettle, add, let's say, some flowers at the back end, at the back. And we also want to, let's say, modify the image to make it ideal for a banner. That's my instruction. Let's pass this and see what are some of the generated images. This will basically modify the image with all the descriptions that I provided, with some variations here and there due to the model looking into those details and generating it. Let's look at those in detail. First of all, this was my original image of some biscuits on a table generated with Stable Diffusion. Now I wanted to modify it by further blurring the background, having some flowers, having some kettles, and make the image a slightly better, and it has added some crumbs on the table. So this is how Stability AI has modified their pipeline with image to image to edit the image. Let's look at another example. We generated this image of an all-purpose floor on a kitchen table with some ambient light. Now let's say I want to change this a bit. I want to add, let's say, an image of some other object beside it. Let's say, for example, a donut. I want to add a picture of a donut resting on it just beside it. So we pass that prompt to image-to-image pipeline with Stable Diffusion, and it edits that image and creates this new one. It's exactly the same image with a donut added just beside it. This is how you can easily generate and edit images using Stable Diffusion, exactly the same model with two different pipelines, and you can modify it for banners, for advertisements, for different products on shelves, for cars, and for different industries without having to manually go through hours and hours of Photoshop or other investments. So we saw all of the details about image generation, prompt engineering to make the image generation better, more detailed, and also image editing to edit finer details in the image. Now, we ran all of this code in the notebook. As you saw in the output was showing up in the notebook. We had to scroll through it, and these are not integrated with each other. We want to build something that is integrated, that is quick without having to go through hours and hours of writing Flask, dealing with course errors and other issues, and we want to do all of this in just one file quickly. And that's where Gradio comes in. That's where we discussed about the details of Gradio, its capabilities, and how easy it is to set it up all in just one file. So we'll go through those details now. As you see on the screen, we have a simple code for Gradio UI. We will go through each of these details and how they have been integrated one by one, all of the aspects of image generation, prompt engineering, and the UI has been built step by step. So starting off, we are loading the details from config. We have the API URL for local deployment. We'll see how to do that and how that works. We have a couple of functions which connect these different aspects and these different modules that we created for image generation, image editing, prompt engineering. And these functions will be called along with uploading and saving the image and connecting this workflow. And we also need to convert the image to base64 because that's how the code handles this and LLMs handle it. And we have the entire workflow defined for it. Starting off, we have base64 to image. So our image gets converted to base64. Then from base64, we are directly converting it back to the image by reading it with the pillow library. Then we have the image workflow. We have the upload image workflow. We have the edit image workflow. And we have the edit generated image workflow. So these will be called in each of the modules that we are going to design with Gradio. We have defined that in build UI. So how do we do it? Step by step. Let's understand it. Starting off with Gradio, we'll first give it a title. The page will have a title. In this case, we are giving it the title Prompt to Image and Editing NIAT Demo. We can choose any title there, and we can also give it a particular subtitle with any font of our choice. That's the first part we are defining in Gradio blocks. After that, let's look at step by step what happens. We want to divide our user interface into different columns, different rows, And then inside those columns and rows, we want to have further boxes inside, and then buttons, and then display of text, output, some suggested output, suggested inputs. How do we do this one by one? We can define them as containers, as flexes, as sketch boxes, sketch headers, and all of these aspects. Let's take a few examples that are defined here. We have a sketch row, which defines the row using a flexbot layout. A flexbot layout is basically, it's like a container within a container, where inside a particular row or column, how we define it, you have a flexbot, and inside that you have another aspect of it where you can mention another box or however you want to design it. Then you have the flex direction, which will align it horizontally. You can align the items depending on whether you want to stretch each of those children boxes into the same height, or you want to keep it the same, or you want to make it absolute coordinates. You can give the gap between boxes based on pixels. You can decide how much the width will take as a part of the container. So for example, you want to design a box within a box where there is significant space outside, you can do that. Then you have sketch call, we have sketch boxes, you have sketch headers. All of these are basically a part of Gradio's sketch theme, where you can use these particular fonts, these particular colors, letter spacing, text shadows to define how you want the UI to look. We'll see these one by one as we deploy this locally and then eventually online to see what the UI looks like and what each of these parts look like. Let's take a few more examples out of this. We want to define a button. So once we, let's say, type in our text, we want to click on a button instead of it automatically executing, and we can define it using Gradio button in just a few lines. This can be modified based on how we want the background color, text color, box shadows, and all of those CSS aspects. After that, we need to create something for uploading the image, showing images. So let's say we want to upload an image and edit the image. That box should be there. We want to edit an image, so an already generated image will be there and want to edit it. So for these aspects, we need to define an image box, and that's what we have done here. And the rest of it are the CSS aspects of it. Let's take one more example. We have a big prompt box here. So depending on what kind of shape you want and how you want to position it. So let's say you want to define it into 3 rows where you have an area with a big prompt box that can auto scale depending on how you type it, or you want to fix it and you want to auto scale the image box. You can define it by coordinating between the size of the text box and the size of the image box. Now this completes most of the aspects of the design, and we simply need to now write the code in Python for each of these design aspects that we defined in the JSON. How do we do that? Well, we have, first of all, we are defining the row, we're defining the column, we're defining a markdown. We can basically write anything we want inside that. We have a text box with a placeholder. So for example, I want to generate an image. For this image, I want to give the user some example. Someone who's using the user interface for the first time, they want to create an image, but they are unable to think of what they should create. They would get an instant idea from the placeholder, which has an example written inside it. Then we have the buttons. We have the engineered prompt section for text box, which will show the engineered prompt as output. We have an upload option where we can upload images in case we don't want to edit an image that has been pre-created or we saved it from a creation earlier. After that, we'll also show the original image that the person generated. And for that, we have a box. We have an edit instruction box so that the person can type in the edit instruction, which gets passed to the edit model that we saw in the previous session. And then finally, we have an edit button. All of these things will be combined together in just one user interface, and all of this can be written in just one file at one go. Now, it is important to maintain the state so that it does not keep refreshing every time. So let's say you have generated an image and you want to use that particular image and everything generated in that state and edit that particular image, it gets saved into the Gradio state and it does not keep refreshing every single time. unlike some other, let's say, libraries where this issue will occur. So Gradio solves that problem. Now, finally, we have the buttons which will execute these workflows, and we are building the UI and deploying it on any specific port. We'll look at how we can deploy this locally and eventually on the cloud. Let's start with locally. As you see, I've defined the port as 8048. You can choose any port which is open and not being used, be it on your PC or be it on the cloud where you're deploying. Then we have the server name. So for server name, if I want to make this available outside, then apart from opening my port and port forwarding it, I also need to mention the server name as 0000 and share equal to true so that it can be shared. When I deploy this, as you'll see now, let's see the steps, how it works. It's very simple. All we need to do is run this code with Python Gradio UI.py. So I will click on run, or I can also type in Python Gradio UI.py. And it will run it on the specific port that I have defined, currently on localhost because it's running locally. You can also generate shareable links by port forwarding it with something like nrock, or Gradio has an inbuilt port forwarding option which is free for 7 days and also payable if you want to use it further. So this is how it is deployed locally. Let's look at the user interface and understand each of the components that we discussed. So this is the user interface that has loaded based on how we defined. To recap, as you see, we have the header at the top, and then we have the subheader. We have each of these boxes for each of the purposes that we designed it, starting with the prompt, where we are defining the prompt that we want to use to generate the image, the engineered prompt, the upload image, the view and edit image instructions, and the engineered edit prompt with the editable image. As you see, the way we created the user interface in the code, the prompt box is within a flex header and it is fixed. And when I click on the button, it gets the engineered prompt, passes it off to the next model, and creates the edited image. This image will be shown in this specific box, which is scalable. This will scale based on the size of your image, how you want to create it, and by default it is 1:1 aspect ratio and for a specific size which is mentioned in the config, but you can change it and this will scale automatically. Similarly, we have the edit instructions. Once we give the edit instruction and edit the image, it generates the engineered edit prompt and it will show it in this edited image box, which once again is scalable. So this is the full UI we built with Gradio in just a very few simple steps in just one file. This is how easy it is to build with Gradio and create user interfaces that are quite nice, sleek, and very quick to deploy and showcase your product. So now that you have seen the UI and how Gradio can easily build user interfaces in a very short span of time, let's get it running. Let's start looking at the backend and how to make it work. So we'll define the backend with the APIs created using Fast API. We'll use the same code that we used for image generation, image editing, and prompt engineering and integrate them together by calling them through APIs via Fast API. Starting with the first part of Fast API, we'll import all the necessary libraries and all the necessary modules for prompt engineering, image generation, image editing. We'll import Fast API and Pillow and other libraries that we need. We'll define the middleware for Fast API so that we can get Gradio to work and allow all of the cross-origin resource sharing and allow credentials in order to ensure that there is no blockage. After that, we'll define a few functions which are needed in order to go back and forth between an image generated by an LLM, which is a base64 string, and showing it in a browser versus going in the reverse direction. So we have defined that using Pillow library, and we are converting images to base64 and then base64 back to image. And then we are defining the APIs. What will these APIs do? So first of all, we want to generate images, we want to edit images, and in between this, the API calls should happen in such a way that it calls those functions that are necessary to engineer the prompt and pass it to the next pipeline. Let's look at how that happens. First of all, we have defined an API endpoint for generate. What this will do is whenever we click on generate button in the user interface in Gradio, this API endpoint will be called, This in turn will call those functions that will load the LLM, and if it's already loaded, it will utilize that and generate a base64 string from the image using pillow. This response will then be returned as a base64 string, which can be embedded as a JSON. We have defined another one for editing. So this editing, two parts. We want to edit our generated image, which is AI generated, or we want to upload an image and call that. Both of these will practically do the same thing with some minor differences. So we have defined two endpoints, one for editing and one for editing the generated image. And what it will simply do is it will take that image, make the necessary conversions to RGB, and then it will pass it to the LLM model for image-to-image pipeline for editing. This will either happen with the uploaded image or the generated image. So these are the three main endpoints that have been called. But if you notice carefully, inside each of these, engineering is being done. So as we saw, prompt engineering is very important, and that is connected in this pipeline so that whenever we are clicking on enter, within this API itself, it goes to the engineer generation prompt or the engineer editing prompt. One is specifically for generating, one is specifically for editing, and it will then pass it to generate that actual image. This will then be returned to the user interface in Gradio, and as you remember from Gradio, we were converting those base64 strings back to an image using pillow and then displaying it back to the user. So this is the combined end-to-end workflow. And now let's start this server. So I'm deploying this using Fast API, and I have named my file as app, hence it is UVCon app. Once again, I want to open this up, so it's 0.0.0.0, and the port that I'm running it is 8047. We can choose any port. In this particular case, I've done 8047. This will load all of the models, that is all of the checkpoint shards, which is basically for your language model, your image generation model, which will be used for both. Image generation model, as we already discussed, gets used for the image generation pipeline as well as the image-to-image pipeline. Once this has been done, Fast API endpoints are now live on this particular port in the local host. Similarly, we are going to run Gradio by using Python Gradio UI.py. So this is now running our front end and back end together, where the front end will hit the APIs at the back end, get the response as JSON, including the image as a base64 string, and that base64 string will be shown to the user by converting it back using pillow. That's the integrated workflow. Let's look at how it works. Starting off, we have the UI. Now I will use this particular prompt for generating an image of a salmon. I'll give some more details before engineering, like 100mm RAW camera, the aperture, details about steam, spinach, lemon, then details about the light, the exposure, how the shot is taken, and it will get further engineered, as you can see, and then generate the image. So this end-to-end pipeline is working from Gradio back to Fast API endpoints. It will call the models, generate them using this engineered prompt, and then finally create the image. Similarly, as we already discussed, it will also connect the edit image instructions, where we can either directly use this image and give some instruction in edit instructions, or we can upload some image which we have already generated or a real image and edit it at the same time. This, once again, in the same fashion, will engineer the prompt, edit the image, and showcase it to the user. That's how the entire Gradio UI, Fast API, and the LLM models and vision models are connected together in one combined setup. So far, we have seen each of the layers comprising of the Gradio UI, prompt engineering, image generation, and editing the images. Now, we need to put this in production. Let's see how we do that on a website known as Runpod. Deploy any model, any aspect of any app, any serverless function as per your need. This is specific for AI models and AI deployments. Let's look at how it looks like. On the screen, you can see these ports which have been exposed on Runpod. This is the user interface of Runpod, where we can deploy any pod, which is basically a virtual machine, or we can deploy a serverless function. In this particular case, we are deploying a virtual machine, and in that virtual machine, we are deploying our user interface and the backend. On the screen, you can see specific ports which I have opened on this virtual machine, which are through which we can communicate via APIs from the external world. In these APIs, we are going to have each of everything integrated, and in these ports, all the communication is going to happen. Let's look at how that is done. First of all, we are going to deploy the backend in the same way we did it locally using Fast API and UVCon. We are deploying it in port 8047. Second step, we are deploying the user interface in port 8048, which is the Gradio interface. These two are connected together, and in the config, we are mentioning the URL to the backend so that the frontend can refer to it and communicate. Now, we'll open the API running in Runpod and we'll showcase an example. So this is the same Salmon example, and let's see how this works in Runpod and how the image is generated. In the backend, when I send this API request by clicking the button, instead of this routing locally, this will go via the server from port 8048 of Gradio, and it will communicate with port 8047 in the link mentioned in the config for Runpod, and then generate the results. So this is the result that we can see in the user interface. So this is how we can deploy both locally as well as in the cloud, be it with normal CPUs, with MacBooks, or with NVIDIA GPUs in the cloud. So now we understood all the end-to-end aspects of how the app works, starting with image generation, prompt engineering, the Gradio UI, and all the aspects of it. Now that we know the full details, let's break it down step by step, layer by layer, and understand how everything is connected. So let's look at the diagram on the screen. Starting off with the user interface. The user interface primarily has our Gradio user interface, along with a few local demo scripts and Jupyter notebooks that we have created for the UI. Primarily, the Gradio UI is having everything in one place to connect all the aspects of prompt engineering LLMs together. So this is the primary UI layer all in one go, which you can occasionally show in different parts if you want. But primarily, it's just one file. Then we have the API layer. The API layer comprises primarily with Fast API as a gateway, which is the framework that is used for creating each of the endpoints. The main endpoints that we have are generate endpoint, edit endpoint, and edit generated endpoint. We have some more function calls inside this apart from generation as we discussed, but the endpoints will start with generation and editing. Editing, that is, either it is for the actual image or the uploaded image as we discussed. So this is our API layer. Our user interface is connected to this API layer. Now, let's look at the next part. Our next part is the core processing, which is the actual work in the backend happening when the API calls are working. When an API is hit, what's the process that happens? The first step that happens is it will engineer the prompt. So whether, as we discussed, whether you are trying to generate an image or edit an image, it will first engineer it first and foremost. Then it will go to the next step, which is generate image or edit image, depending on how we want to proceed. So let's say you want to generate an image of a salmon, as we saw, it will generate that first, and then you want to further edit it and refine it, it will go to edit image. Or we can also upload an image and edit that image directly. So this is the core processing that is happening, which we saw both in our local demo as well as in our Python files that are connected to the UI. Lastly, we have the main aspect of it without which the entire process will not work, and that is the models. We have 3 different models, technically just 2, but depending on the pipeline, 3 as we discussed. First is our large language model for prompt engineering, specifically Qwen2, which is stored in this particular folder as you see on the screen. And we have our image generation and image editing models. In this case, both of them are stable diffusion, pointing to the same model with a different pipeline. So this is our full structure end-to-end, layer by layer, that are connected with each other, and it functions starting from the user interface to the API layer to the processing, the model storage, and then back to the UI in the same direction. So that's how the entire process works. All right, we have come a long way from a raw Jupyter notebook to polished, shareable Gradio apps. We explored how Gradio accelerates user interface prototyping in pure Python, the art of structured prompt engineering for both text and images, and we also looked at how we can build modular demo components without front-end code. We also looked at how we can embed AI-powered editing for real-time refinement and how to deploy our unified app with minimal overhead.